Mary McIntyre.
And Neil Norman.
Then we have 2021 D1 Swan. That's currently MAG 11. That is fading observable 55 degrees north to 14 north. And that's an early evening object, last visually observed in April 2021.
Next is 2020 T2 Palomar, magnitude 11.5 and brightening, 70 degrees north to 30 degrees south, an all-night object, last viewed in April.
Then we have 7P Pons Winnock, and that is MAG 12.5 question mark. That is brightening, observable 70 degrees north to 65 south. That is a morning object, but not yet visually observed.
And next is 2019 N1 Atlas, magnitude 12.5, now fading, 20 degrees south to 80 degrees south. It's an evening object and was last visually observed in February.
Then we have 29P Schwarzmann Wachmann. That's MAG 13 question mark. Obviously, that varies, as we all know. Currently at poor elongation. Last visual observation was January 2021.
And next is our old favourite, 2017 T2 Pan-STARRS, magnitude 13.5 and fading. Now 20 degrees north to 80 degrees south, a morning object, and last visually observed in September 2020.
And finally, we have 2021 A4 Neo-Wise. That is currently MAG 14 and fading. Observable 20 degrees north to 50 degrees south. That is best viewed in the early evening. Last visual observation was March 2021. So it went so well too.
Sure, I'll go first. I'm Carl Hergenrother. I'm currently working at a company called Ascending Node Technologies, which is a new startup to develop software to help plan and support future planetary spacecraft missions. Before that, I spent a long time at the University of Arizona, where I was involved not only in observing and studying comets, but also as part of the Catalina Sky Survey, where I was able to discover a few comets myself. And for much of the past 10 years, I was part of the OSIRIS-REx mission, which was a NASA mission to go to a carbonaceous near-Earth asteroid named Bennu, collect samples from its surface, which we did back in October. And the spacecraft soon, in the next couple of weeks, will be on its way back to Earth. In addition to all my professional work, I've been an avid, backyard amateur astronomer going back to even my grade school days. And I've been observing comets and doing magnitude estimates and sending them to people like Dan going back to, I think, my high school days, about 14, 15 years old. And I still do a lot of comet observing. The coordinator for the comet section of the Association of Lunar Planetary Observers. And I'm also involved in a few other kind of citizen science amateur professional groups like the American Meteor Society and the International Meteor Organization.
Okay, I'm Dan Green. Many of you have heard me before on this podcast. I'm director of the Central Bureau for Astronomical Telegrams and editor of the International Comet Quarterly. I've been involved with comets for a few decades, going back a ways, and not quite sure what more to say at this point, but.
Mm-hmm. Thank you.
You go first, Neil.
Might start with Carl. We'll talk about your comet discoveries. I believe you've had 3 comet discoveries.
Yeah, actually, I've had 4. 3 have my name, and 1 was discovered, but it was kind of questionable as to whether or not it was a comet, and so it actually is called Comet Catalina.
Ooh.
I didn't know that, Carl.
Yep.
That's a crying shame.
Well, I mean, to be honest, what happened was it was at a time where we were considering, because as an asteroid survey, like groups like the Catalina Sky Survey, Spacewatch, even Atlas, if the observer recognizes the object as a comet upon discovery, they will allow the observer to have the comet named after him. Other surveys like Linear and currently Pan-STARRS does this, where regardless of whether the object was recognized as a comet or not by the observer, they're all named after the survey. And so at Catalina, we were naming them individually. And then we decided, well, let's just name them, as a group effort, let's kind of name them all after the survey. And that was my one discovery. And then after that, we decided, let's incentivize everyone and, kind of reward everyone. So let's go back and name them after the observer. So yeah, we're fiddling around with how we wanted our comets named, and that resulted in me losing out on having my name on one comet.
I didn't realize that had happened, Carl.
Yeah.
Interesting. Yeah, we leave it up to the surveys. I think we discussed this in the last podcast that I was on, that we leave it up to the surveys to kind of decide how they want to handle that. And some of the surveys allow observers to have their names on comets and others don't. And the prerequisite is that one observer does basically all the work, though. If there are 2 people from a survey, they're not allowed to get their names on the comet. That's not the way it used to be, but that's the way it is now.
Yeah.
I think it's quite nice to have the personal touch, isn't it? Because I know people quite often comment that it feels clinical when you just have Catalina, 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 and to actually have a person's name there makes it feel way more personal.
I agree
100%.
Yep.
Yeah. I agree as well. And I do miss the days of having, 3 names on a comet. It's happened very rarely now.
It's still allowed. But it's very rare. And 3 is the maximum, and it's discouraged in the comet naming guidelines.
Yeah, I think the last one we had was the last comet discovered by 3 amateurs, independent amateurs. That was the Makolt's Fujikawa Iwamoto back in late 2018.
Yeah.
Araki Alcock.
Yeah.
Yeah.
That was a nice comet, 1983. Yeah.
Correct.
Yeah.
Yep.
Yeah.
Now that happens
IRS
a
is an
lot more
infrared
often with NeoWise.
Ooh.
Correct. So a lot of those, I probably have discovered a couple thousand asteroids. It's just most of them were done when I was at the Catalina Sky Survey, and it was all digital with a CCD. And so they're not actually tracking the individual discoverer for those. So those 33 that are listed under my name, a lot of them were discovered before there was the Catalina Sky Survey. There was the Bigelow Sky Survey, which was primarily me and Tim Spar with Steve Larson supporting us doing a photographic survey. And out of that grew the Catalina Sky Survey. So a lot of those discoveries go back to the old days, just using, Fuji T-Max 400 film with a 16-inch Schmidt telescope doing 8-minute exposures. And that's how we discovered, and we were in particular looking way out of the ecliptic, so we weren't competing with the Shoemaker's group or Eleanor Helene's group. So a lot of the objects we discovered were Hungarias and Phocaeas and high inclination objects. And it also resulted in us finding a nice near-Earth asteroid, 1996 JA1, which got up to 10th magnitude and almost came within about 1 lunar distance, as well as my first comet, which was Hergenrother Spar back in 1996, came from that photographic survey. So interesting story about that. So this was September 1996, and it was kind of a hazy, cirrusy night. I sometimes have the habit of leaning towards being the lazy one, and decided I didn't actually want to survey that night because, well, it was kind of cruddy and we weren't going to go quite as faint. And Tim kind of yelled at me and guilted me into observing. So I went and shot a few images. And as it turned out, because there was a sucker hole, so we were aiming for the sucker hole, and a lot of famous objects were discovered in, sucker holes in the sky. And by the second image, we would take 2 images about half hour apart. Second image, the clouds came back in and didn't go quite as deep. And so we, went and developed the films. And the next day, Tim's like, "Are you going to search those films for stuff?" And I'm like, "Why? Why should I bother? The clouds came in. We're not going to see anything." And again, he guilted me into looking at the images. And I said, "Well, we didn't go faint, so I'm just going to look for fuzzes and streaks, comets and near-Earth asteroids. I'm not going to care about main belters." And so I'm sitting there scanning along, and we used a stereo microscope at the time, which was actually built around an old tank site that Steve Larson had found. And I'm scanning around, and I came across a fuzzy streak, and immediately stopped, and my jaw kind of dropped. And Tim noticed that I was talking and complaining probably, and all of a sudden I got real quiet. He's like, "Oh, you found something?" And it's like, and I probably used an expletive there or something, but yeah, saying I found a fuzzy streak, and that was our first comet, and it was a long period comet that was about 10th, 11th magnitude at the time.
So were you just taking one picture and looking for something that hadn't been tracked with the stars then, rather than doing a blink over a different time period?
Well, that one, usually we took 2 images. Each image was 8-minute exposures, and they were about half hour apart. So I did have a pair of images here, though the second image didn't go quite as faint because the clouds had come in. But with the stereo microscope, anything that moves kind of floats.
It's a lesson there for people that think, "Oh, I can't be bothered tonight."
Exactly.
Yes. Yes.
Oh yeah,
I had that the other night.
yeah. Even here in Tucson, I had one night where we got 6 inches of snow, and there wasn't a cloud in the sky. And for a few hours, I was really perplexed why it's snowing, and I can see the Milky Way and the stars. And then finally, I looked at another mountain range and noticed that we were actually above the clouds, and the wind was blowing the snow up out of the clouds, and it was falling onto the mountain peaks.
Wow.
Oh my word.
That was pretty fun.
I've one very great memory of I was just out in the early days of my imaging in my pajamas with a telescope, looked over my shoulder and I was like, oh God, all this haze is coming up. There's all this red light pollution. It was aurora. And,
Oh yeah.
and I don't live in a high latitude place here. I'm in Oxfordshire, so that was the first time I'd ever caught aurora from the UK, and I've done it a dozen times since. Now I know it's possible. It's any chance at all, and I'm out. So it's.
Well, you're a lot further north than we are.
Yeah, probably am. Yeah, we're 52 degrees, so
Yeah,
more
I'm
chance than
only
you
at
guys.
42 in Boston. Yeah.
Yeah, I'm 32 in Tucson, and I saw the aurora once from the telescope. And when I say I saw the aurora, I kind of saw a reddish blue glow on the horizon. That was about it.
That's enough.
Yes.
And
Yeah,
it
there's
hasn't
nothing
gotten
wrong.
any better.
No, no, I don't think it's going to get any better.
Hmm.
Yeah,
Yeah.
we discovered it. I can't remember the exact date. I know it was September. Yeah, or first few days of September. I remember it was in Pegasus. And again, we were looking about 30 degrees out of the ecliptic as we usually did. And it was just going right through opposition. Yeah, retrograding, pretty fast clip.
Yeah.
Yeah, and that was one where when we discovered it with the Schmidt, we were able to use the 8-inch finder scope that we used for visual guiding at the time, and we're able to see it visually, which was kind of nice.
Mm.
I have been able to see 3 of my 4 discoveries, though one I had to cheat and use a 1.5 meter telescope to catch it at 17th magnitude, but could see it.
Mm.
Yep. Yeah, so
Oh.
that was discovered after the Catalina Sky Survey had been founded. So now instead of using film, we had at the time a 4,000 by 4,000 pixel 4K CCD. Now I think they have a 10,000 by 10,000 pixel CCD. So that had about a 3-degree field of view. And we at that time still didn't quite have our automatic detection software going. So we were still just blinking images kind of manually and looking at the images. And we would take 3 images, again, a few minutes apart, and I was blinking them and saw this, faint fuzz up in the upper right corner of the image. And it turned out to be 168p. And that was kind of cool because when I ran the orbit forward, I'm like, oh, this object, which I think only got up to 16th magnitude at discovery, was going to get brighter I think was it 2006 or 2007, 2008, can't remember the exact year, was going to have a pretty close approach to the Earth. And so it might get up to like 12th or 13th magnitude. So I'm thinking, oh, great, maybe I can see this visually. And who knows, maybe it'll outburst and I'll be able to see it from my backyard and my big binoculars. And of course, that's exactly what happened. It went into outburst. I got up to about 9th magnitude. I was able to see it in my 30 by 125s from the backyard. It shed a few pieces that I was able to convince a few friends of mine who had big telescope time on Kitt Peak to observe. We send the observations to Zdenek Sekanina, so he can kind of figure out when the splitting events happened. But then 168P was supposed to come back, I think last year, or 2 years ago. Yeah, actually it was pre-COVID. Geez, it's already been 2 years. And of course, it never came back.
Oh no.
Probably disintegrated.
Yeah.
Mm-hmm. Yes, I remember I remember going through my news feed on my phone, and there was this article about, super bright comet to be observed tomorrow night. And I'm like, and I'm going, I wonder whose comet this is. And I'd be like, I hope it's not mine. And I'm going down, and like 168P Hergenrother is going to be like negative 18th magnitude. I'm like, oh no. And I had people at work at the University of Arizona congratulating me. How my bright comet, they're going to go out and see it. And I'm like, don't bother.
Oh, no.
Well, we still haven't learned from that mistake.
No.
Yes. Right, but the interesting thing is, at the tail end of that year where it fragmented and had the outburst, it still looked like a healthy comet months later. It just showed signs of just shedding some pieces, which comets do from time to time, and it doesn't mean the comet completely disintegrates. So something happened out aphelion time frame where it just completely fell apart or went active. I mean, we've had comets like Perrine Mercash is a good example, where it was seen and then missed for a few apparitions, and seen and missed and seen and missed. So you don't know.
Hey.
Right.
Hey, Carl, I just pulled up the on the MPC website. I make sure I got the right comet here. Is this 168P?
Yes.
Yeah, they've got 2 observations from January 3rd of last year there. Two single night observations from CompuStar Observatory in Rouen, L59 observatory code at 19.9 magnitude. What's going on there?
I don't know if those observations are of the comet. I do remember when those 2 were published in the Minor Planet Circulars, but no one else was able to confirm them. So I wonder if it was just they happened to be observing.
Yeah,
and
but I'm like scratching my head. Why did they publish them? Why would you publish 2 observations on one night when the previous observations were in 2013?
Do not know.
That's bizarre.
I don't think those observations correspond to the comet.
Right.
Bad.
Right. Yep. Right. Yeah. Okay.
Seems unlikely, doesn't it?
Yeah,
it does.
Another thing to point out to the MPC.
Yes. I was just going to ask Dan, actually, because Dan's the man in the know. Is there anything on the possible comet confirmation page of interest, or anything coming up?
I haven't looked in the last 24 hours. There have been a bunch of things posted there. What, like 9 or 10 objects right now. All the reports that I have been seeing coming in on these objects are saying that they appear stellar. I'm not seeing anything saying cometary activity on any of them. I see there are two that are brighter than magnitude 20.8. So most of them are very faint. There's a couple right around 19.3, 19.4. And but I have not seen any reports of cometary activity from these. So nothing.
They'll get the dreaded A designation, won't they?
I'm sorry, what?
They'll get the dreaded A designation.
No, not necessarily. Yeah, I think we talked about that last time, but the MPC has not really put out guidelines as to when they should use A/, and they've been kind of arbitrary, but they basically are putting out objects with the A designation when orbits are nearly parabolic.
Yeah.
So.
Yeah.
Sure. So OSIRIS-REx actually began back in 2004 when we submitted our first proposal to NASA. And at the time, it was the Discovery class mission. And I was brought on board to actually help select the target we would go to. And for the first proposal, we were going to go to a completely different near-Earth asteroid, which, hindsight, now that we got more observations of that asteroid, was not carbonaceous at all. So it's a good thing we didn't go to that one. But September 2005, all my big discoveries seem to happen around September. I was observing this asteroid called 1999 RQ-36, which was making a close approach to Earth. It was like 15, 16 magnitude, which is, pretty bright for a near-Earth asteroid and easy for a 1.5 meter telescope. And when it got light curves, colors, realized it was a B-type asteroid, so it's carbonaceous and slightly blue. I was intrigued and interested because B-types, like Phaethon's a B-type, and a parent of the Geminid. Wilson-Harrington, which was an active comet for 3 days in 1949, B-type asteroid. A lot of the main belt comets, like Else-Pizarro, 176P linear, they're all B-type asteroids as well. So I emailed the PI, the principal investigator, head of the mission, and the deputy PI, and said, hey, I've got this great object we can go to. And it's carbonaceous. It's a B-type. It could be related to comets. And we've got radar. A lot of people hadn't published their data, but a Google search showed that there was spectroscopy and radar and a whole bunch of other great data on this object. And that is the asteroid that eventually was named Bennu. And that's the one we actually went to with the OSIRIS-REx mission. So we launched in 2016. We caught up to the asteroid tail end of 2018 and spent all of 2019 and 2020 kind of observing the asteroid from different distances and observing geometries, and did a complete global map and photometric survey of the surface. Discovered that even though, yes, it is a dark carbonaceous object, there are pieces of much brighter material on the surface, like potentially pieces of other S-type asteroids or even pieces of Vesta sitting on the surface of this asteroid, which was pretty cool. And early on, about a week after we had dropped into orbit, and it was a really tight orbit, we were only about 1.8 kilometers from the center of this half-kilometer diameter asteroid. We were, every day we're taking navigation images, and I was just blinking through the navigation images, which were about 30 by 40 degrees on the side, go down to about 7th magnitude. And I'm seeing, the constellations go by. There goes Orion, there goes Lyra, as we're going through our, about 3-day orbit. And then all of a sudden I see what looks like this star cluster sitting right off the northern limb of the asteroid. And it's no star cluster I recognized. So I'm saying, well, maybe it's something in the southern hemisphere, which I'm not quite as, acquainted with. But pulled up Stellarium, looked at where we were pointed, and like, this is Hydra. There's nothing in Hydra that looks like this. And then as I played around with the images, quickly realized that what I was seeing was hundreds of particles being ejected off the surface of the asteroid. Wow. And that was the first of these major, we call them particle ejection events, that the asteroid seems to experience quite routinely. Anywhere from 1 to 1,000 particles being thrown off the surface every day. And some of these particles we were able to follow, they were actually went into orbit around the asteroid for up to a week, made maybe 24 revolutions around the asteroid. And so I spent most of the last 2 years on the mission characterizing these particles, and they're small. We're talking millimeters to centimeter sized particles. And the only thing that we can think, the only two mechanisms that we think are actually producing them is one, it could just be micrometeoroid impacts. That the stuff that produces nice meteors here, of course, there's no atmosphere around Bennu, so they're hitting that surface at 20, 30, 40 kilometers a second, and that's enough energy to throw off these particles. Or possibly the rocks themselves are kind of fracturing as they thermal cycle. As the asteroid rotates every 4 hours, you're getting cracks, and those cracks in a microgravity environment are energetic enough to throw particles off the surface. So it's kind of cool, because what it means is that probably every small asteroid is experiencing these. And if you're looking for them, you now have test particles in orbit continuously around every small asteroid. So you can watch these test particles and actually get gravity fields and gravities out of just observing them.
Wow, it's so interesting.
Yeah.
(168p). Just because it's periodic. I like periodic comets that come back. I like that it, had an outburst and it fractured. And honestly, I think it's kind of cool that it disintegrated. I actually like disintegrating comets. I think you can learn a lot about comets just by how they fall apart. And we have been learning a lot from ISON and other comets. You can, figure out exactly, their strengths, how large the object was when it broke up. So it tells you a lot about just the internal structure of these objects to begin with.
Which
yeah, it's
comet
interesting, isn't it? Sorry, go on, Neil. I think you're probably going to ask the same thing I was about to ask.
I don't know. What I was going to ask Carl, because we always ask the question, if you could choose a comet to send a mission to, like you did your OSIRIS-REx to Bennu, the asteroid, which comet would you send a probe to land on, or to just circle around? I
would have picked my comet 168p because I had a recent outburst and pieces came off. But I would go to 73p Schwarzmann-Wachmann 3 in the C component. That was the one that had the major splitting event in 95. And the secondary components continue to keep splitting up. And I think the last time around it had another piece that broke off. But they were able to observe that one with radar. And so the C component is about 1 kilometer across. The B component, which may or may not still be with us, but when the radar observed it, it was 1/3 of 1 kilometer across. So if you go to C, there should be a huge kind of pristine area of that surface where the B component broke off of it. And that would be pretty cool. And so when you get such a large piece breaking off of what's really a large comet, you wonder, did it look a lot like 67p, where you kind of had two pieces glued together? And in the future, I would think that neck would probably finally give way on 67p, and you will have the major, the primary, and then the smaller, the head of the duck would be the secondary that goes off and may even disintegrate completely eventually.
Yeah, that bilobar structure seems to be really common recently. A lot of stuff we've seen seems to have that. Ultima Thule had it, 67p had it. It seems to be quite common.
Yeah, definitely does.
Is this because, obviously because of, I don't know if you guys have followed in the USA, but we had a really bright fireball in the UK recently, and the meteorite was recovered really quickly. So it's been big news, and everybody's been talking about carbonaceous chondrites, and it's just been everywhere. And one of the things that I don't think I'd really realized until reading a lot of stuff on this is that a lot of asteroids aren't just like a kind of, they're made up of lots of different things that have broken up and then re-annealed and broken up again. And so rather than having a solid structure that is its own parent body, it's made up of loads of other different fragments of things. And I guess comets are a bit different than that. So it's quite interesting to get the the sample return missions to compare structures like that? Because I guess I'm right in thinking that most comet meteors don't ever really survive to land on Earth in terms of meteorites.
I think that's erroneous.
Oh, okay.
I know that's stated a lot, but I think it's very unlikely that we don't have pieces of comets in our meteorite collections.
Oh, that's good to know.
Comets have they have pretty solid rock, and there are comets that really are quite well held together. I mean, you look at some of the sun-grazing comets that have gone really close to the sun without any substantial breakup, and we have spectroscopy of them that shows a lot of iron, for example. So I would be. I think it's foolhardy to say we have no pieces of comets in our meteorite collections on Earth.
That's interesting.
I mean, we'll find out when we get the first comet sample return mission. I mean, even for like with OSIRIS-REx and Hayabusa 2 both going to carbonaceous asteroids, you wonder how much of these carbonaceous bodies, when they enter the Earth's atmosphere, how much of it actually survives? Are the carbonaceous chondrite meteorites really representative of those bodies, or is that just the strongest 1% of that initial fireball and all the weak stuff gets disintegrated and burns off?
Oh, the great thing about the Winchcombe fireball is that as well as being, we actually had a rare clear night across the whole UK. So it was caught on camera on 6 different networks. And as well as that, one of the guys within the UK Metro network had a diffraction grating on it. So not only do we have orbital details, we actually have a spectrum, we obviously have the videos, there were countless doorbell cameras and goodness knows what else that caught it. And I don't think there's ever been so many visual observations of a fireball from the UK either. So this we've got a lot of information on this fireball, so I think it's going to be useful in piecing together that exactly that, what survived, what was it likely to have been before. And we've got nearly a kilogram of material of this thing already. So, and it was recovered very, very quickly. So it's pristine. They're comparing it in how pristine it is with the Hayabusa 2 stuff. And they've got nearly a kilogram of it, which is just extraordinary.
Do you know the date?
People busy for a long time. The date of the fireball?
Yeah.
I will double check because my brain's gone to sleep.
Just in the last month or two?
Yes, fairly recent. Yeah. We caught it on our camera as well. I'll just quickly check my Flickr page because I think I put our video on my page.
I think it's late March, wasn't it?
It was. I think it was the very end of March.
Okay.
About the 29th or something like that, I think.
Mm-hmm. And do you know where the meteorites were found?
Yeah, they were found in Winchcombe in Gloucestershire.
Oh, okay.
Yeah. Thank gosh, this year's going so fast already.
It is. That's right.
Most of it is actually the people that found it donated everything to the Natural History Museum, which is just lovely of them.
I remember hearing news stories about the fireball, but I didn't hear the follow-up stories about finding meteorites.
Oh, funnily enough, their daughter heard something thunk on the drive and didn't really think anything of it. And then the following day, they'd seen this black kind of spatter pattern on the drive, and it looked like somebody just upturned a barbecue on their drive. And she'd emailed her son, and basically the son was like, it's been on the news that they're looking for samples because of COVID. They couldn't send the usual search teams out, so they actually released the strewn field information because it was also like 60 square miles of farmland for the strewn field, and they obviously didn't expect to find anything. And luckily it landed on the drive. Some of it bounced into a neighbour's garden, some of it went onto their lawn. But it was really weird because it kind of just disintegrated into a pile of powder in the middle of the drive. And I believe they're actually going to be removing that section of drive to go into the museum because it's actually more interesting than the rock, because the rock's just a dull black rock. So
that's funny. You know,
it's an incredible story.
The Peekskill meteorite in New York was it the early 1990s or something, that ended up going through the trunk of some high school girl's car, and the car ended up being sold for a fair amount of money to a museum.
Yeah, I think, funnily enough, this family said they normally park their car on the drive, and if they had done, their car would have been worth significantly more than the meteorites would have been. But no, it's been an amazing opportunity to have so much data on one object and be able to actually like have an orbit for it. And it obviously a spectrum is going to tell us quite a lot, and we knew its original mass, and there's going to be a lot of work on these meteorites. They're already being shipped around the world, and there's stuff going on. So no, I think we don't get lucky and have something like that happen very often, so we need to send probes to places to do it. But there's been a kilogram recovered from surrounding areas as well altogether. So none of them are big fragments, and one of the bigger ones was lodged in some soil and it split in half as soon as they touched it.
Oh.
But they do know what class it was, but that's still embargoed. I think we had a catch up on Zoom with the Natural History Museum guy, that Ashley King, the other day, and they haven't released that yet. So they've asked us to not say, but it's amazing. I mean, I still, the fact that we got this on our camera was just extraordinary, and I still can't quite believe it happened. And to find something that was a rare meteorite from it as well was just
What kind
extraordinary.
of camera? You have an all sky camera or something?
No, the All Sky Camera Network did get it, but we've got the Raspberry Pi Global Meteor Network cameras. We have one of the original UFO ones, but they're just these little Raspberry Pi powered cameras. They've got about a 90-degree field of view, 90 by 45 degrees. Because the wider angle can cause distortion that makes it difficult to analyze the data with that system anyway. So yeah, they're quite low cost for kind of under £200. You can be set up with this system, and it all the data uplinks automatically every morning. It's a really fully automated system, so you don't have to sit and crunch all your data yourself and do the analysis and weed out the junk. It kind of it's all run on the cloud, and they have these really smart engines that run through and weed out the aircraft trails and satellites and all of that junk. So it's a great system. We've upgraded, and we've now got 3 of those that are Raspberry Pi and 1 of the old type that we will upgrade again at some point.
Awesome.
It's the first carbonaceous chondrite ever found in the UK. It's been a big event for us here, so I think we'll be dining out on it for some time.
So the British Museum has it?
The Natural History
Museum.
As soon as it's open, they will have some of it on show, which is great. I really want to go.
Yes. Yeah.
Yeah, definitely. I was able to watch a meteorite fall actually from my driveway once. I was out.
Really?
Yeah, this was, what was this? 2006, 2007, 2008. I can't remember again. But yeah, I was out there looking for a comet. I had my binoculars and I was looking for, I think, one of the comet Gorads that was running around at the time. And all of a sudden, something was shining in my eye, and I thought it was my next door neighbor shining a flashlight at me, being goofy. And I looked up, and of course, I don't have my glasses on because I was using my binoculars, and of course, the whole sky's got this big blue-green trail. And I put the glasses on real quick, and yeah, that ended up being the Whetstone Mountain Fall, and I was able to buy a small piece of it so I can have it in my collection of 2 meteorites that I have.
Cool.
Yeah, that was cool. And I had another near miss where I was outside again looking at, I believe, Comet Ison, and went back inside. And I'm in my office where I'm talking from right now. Window points to the north. It was still dark outside, but all of a sudden the whole cul-de-sac that I lived on lit up. And I didn't think anything of it other than, well, who's driving around the cul-de-sac at 4:30 in the morning? And I looked outside, didn't see anyone. I'm like, that was weird, interesting. Didn't think anything of it. Then an hour or so later, I had to get in my car, drive to the airport because I was flying for an OSIRIS-REx meeting. And I look above to the north of Tucson and I see a contrail. And it's obvious that it's either something was going up or coming down contrail. Because we do get those contrails from the launches from White Sands or Vandenberg. And at first I thought it was a launch. And I'm like, wait a minute. There's no launch sites north of Arizona. They're always to the east or the west. And I'm like, I wonder if a fireball happened. So as soon as I got to the airport and parked the car and got my tickets, I'm like, looked up online and lo and behold, there was a major fireball event. So I caught the results of it, as well as the flash, without realizing
it. The number of times I've seen some amazing fireball and my camera is just slightly off to the other side of where it happened. It's just so infuriating.
Mm-hmm. Mm-hmm.
That's very understanding of them.
It is.
Right.
Oh, right. Not that you look like one. I see. Oh, I see. I see. Oh.
So Dan, I don't think I was here last time you was talking. I was just interested in the archiving and stuff that you do for Comet Quarterly. What are you looking at historic data as well, or is it all just new observations that you're archiving and cataloging?
We have done historical data in the past. Most of what has been done is just trying to keep up with current data. But we did.
There must be a lot of it nowadays.
Yeah, but back in the 1990s, I believe it was. Actually going way back, even back into the 80s, we got all of the data from the ALPO, which Carl now oversees. Although I think all those data files disappeared, right, Carl?
A lot of them pre the 1980s have disappeared. Yeah.
Yeah, nobody knows what happened to those, but So anyway, I was lucky enough when Dennis Milan ran it back when he was at Sky and Telescope magazine. He ran it in the, I think, late 60s through the 1970s and into the early 80s. I got all their files and basically digitized all the data. And then I did the same thing with the British Astronomical Association data with Jonathan Shanklin helping out there mostly. And then we've done that with a lot of other groups around the world over time, getting data going back mostly into the 1950s, because there aren't a lot of data that groups have prior to that point. So most of the data that you have prior to that point are problematical observations that you find in the literature. And we've done a little bit of that over time, but most of what we've done going back in time, really old stuff, is like, for example, when Halley's Comet was around in the 1980s, Charles Morris and I did an extensive light curve on the historical data on Halley's Comet, and went back into the literature and pulled out as much stuff as we could get from the 1910 apparition, for example. We have that all digitized in the archive. But the whole concept of the brightness of a comet has been not entirely objective over the decades and centuries. So that was one of the things that Charles Morris and I set out to do when we set up the ICQ archive in the 1980s, was to get some standardization. And of course now there's so much going on with CCD observing, and we get a lot of CCD magnitudes, but there still are a lot of visual total magnitudes of comets that are made by very experienced observers, and Carl's one of them.
I think as a beginner, it's really hard to actually estimate the magnitude of a comet, isn't it? Because it's not as easy to do as doing astrometry on a star or an asteroid or something.
Right.
With the surface brightness and the size can just really mess with your head.
Yeah, that's right. And you basically, there are different methods that you can use where you're basically defocusing comparison stars to about the size of the coma that you're seeing with the comet. And but it can be very tricky. But good observers who've done it a long time get pretty consistent results, and you see a lot of consistency between observers as well. But there's still a very large difference between total CCD magnitudes of comets and visual magnitudes we normally see. And that has to do with a variety of issues, I think.
So do the visual ones tend to upgrade them or downgrade them?
Visual magnitudes tend to be brighter than CCD magnitudes.
Okay.
Comets.
Mm. Yeah.
Yeah, and there's a big problem with CCD brightness of comets, is that the vast majority of CCD magnitudes of comets come from astrometric work. So astrometric work, typically you're tending to underexpose comets a lot of the time, because you want to just get that central condensation that you're going to measure for the position.
Yeah.
And so people that focus on brightness of comets with CCD cameras tend to be few and far between. There are some, and there are some good ones, but most people are doing astrometry first and magnitude second.
That's great to hear. Yeah. Yeah, but I kind of do both now. I do both visual and CCD photometry. And I noticed for the CCD stuff, I usually use the iTelescopes network. And I try to stick with the they have the 106 millimeter refractor, wide field refractors. I kind of try to stick with those for most of my CCD photometry. Of course, that limits you to comets that are got to be brighter than about 14th magnitude to get anything good.
Mm.
Yeah, we've got a huge backlog of points there at the moment. We need to use up.
That's what I did. I picked one of the kind of, not the lowest plan, but somewhere second or third tier from the lowest, and then didn't use it for a year or two. It can be worth it, though. It's, when something like NeoEye shows up, then you're like, oh, I can't actually schedule any observations because everyone else wants to observe NeoEyes. Yeah. Mm-hmm. Great. Looking forward to it. Right. Yeah, and that's one of the problems with observing comets, especially visual stuff, where of course you can't visually, remotely observe something visually, is that if you live any place with a lot of light pollution, you just can't see these comets through your telescope. Even a comet like when Vertin in 46P got up to 6 magnitude. I knew people looking with 10 by 50 binoculars from light polluted cities couldn't even see it.
Mm-hmm. Yeah. Mm.
Hmm.
Yeah, I don't think that LED lights are the great thing that people build them to be. The amount of bounce back from the road is just awful. And they're also blue rich. They're absolutely horrendous for wildlife as well. And it's luckily our street lights are turned off at midnight, except where there's a bend, because apparently headlights don't illuminate the road. But anywhere in the village that has a bend in the road, the lights are on, but otherwise they do get turned off, and it makes a difference. The Milky Way is definitely more visible when they do that. So
Yeah, it's interesting out here in Tucson, which is also the International Dark Sky Association is based here. And they did an experiment with the city of Tucson where they had the city turn all of their street lights down by, I can't remember what percentage, a few tenths of a percent over the course of a week. And then they measured the light pollution, and maybe it was at the half level. And they discovered that the streetlights only produced about 20% of the light pollution. The majority of the light pollution is coming from really businesses and schools. Schools out here, we got these giant football fields. They're lit up bright as day. We got car dealerships where even when they're closed at night, light up the lot as bright as day.
Why do they do that? It's so annoying. And pubs as well, they put outside lights that are just pointing straight up into the sky, and it's like, stop it.
Yeah, car dealerships are worried about theft and damage, but they could have motion detectors, infrared cameras and things. They don't need to use optical lighting for that.
Well, it's been proven that crime rates drop here in the UK when they turn the street lights off because criminals need to see what they're doing. And actually, burglars love security lights because they can see everything in glory detail. So
yeah.
I think the next battle is going to be satellite constellations. It was that report published last week that stated that satellites are actually going to cause an actual increase in light pollution in the sky because of the quantity of them, which is very worrying.
Yeah. There are a lot of surveys that are having troubles getting every night. There's so many photographs that are messed up with satellite streaks now. And
the algorithms are going to have to get better, aren't they?
I don't even know what Elon Musk's satellites are going to do, but.
Well, if it was just that, it'd be one thing. He wants to put 42,000 up there, but there must be 6 other companies now saying that they're going to put their own many thousand strong mega constellations up there. It's just insane.
Right. There's no regulation. Yeah.
No, it's bad.
Well,
Yeah,
they've set a dangerous precedent by saying, just do what you want.
God.
Except it's not actually free. Yeah, which is absolutely out of the question for the very communities that they were billing this as bringing internet to. Nobody's going to pay that to watch cat videos, are they? Let's be honest.
Unless the government funds it.
Yeah. And by using those services, you're forfeiting all your rights and all your privacy. That's where they really make the money.
Yeah.
Taking your streaming, what you're looking at, where you're shopping, selling all that.
Yeah.
Well, the interesting with comets is they kind of, it depends on if we get a bright comet. I mean, Dan was kind of speaking to this before when how many people were submitting visual observations. And the peak was 1996, 1997. And of course, that's when we had 2 really good naked eye comets. And we're kind of almost like in a lull right now. Other than NEOWISE, we haven't had many really good comets lately. And it does seem like there's less and less people getting involved in at least producing, say, magnitude estimates of comets. But all it takes is another big, spectacular comet. And NEOWISE, as good as it was not I don't personally feel like it was a great comet because visually it didn't have much of an impression to me. I could see it naked eye, but it was a smudge.
Yeah.
It wasn't a Hale-Bopp or Hyakutake by any stretch.
Right.
Yeah, I was thinking after the dearth that we'd had before that, we were all very excited by NEOWISE, but a lot of the, whenever there's anything happening, I always send out stuff around the village and get people out looking, and most people couldn't find it. And to me, it was just kind of glaring and very exciting, but people just couldn't see it. So we do need more of that, I think.
Well, in the public takes a lot more to become interested in this day and age, because everybody's so blinded by artificial things. I mean, lights are bright at night. People are used to firework displays, things like that, and so a comet that's even on the order of Hale-Bopp brightness, minus first magnitude or something, is not really going to grab the general public very much. And
I think it's actually the downside of imaging becoming so accessible for people is that visual astronomy is very underwhelming, because people expect to see what they've seen on their computer screen, and that is just not what you're going to see with any astronomical object other than the moon maybe. But even then, you're not seeing the detail that you see after a stacked image has been made.
That's definitely true.
Yeah, and that's an interesting point, because I have a lot of people who I know observe comets, and I'll ask them, submit your observations to the Outpo, to the comet section. And quite often what I'll hear is like, well, my pictures aren't very good. Doesn't look like more than a smudge. It's not as good as, Damian Peach's images or Mike Yeager's images, which is great images. And the funny thing is, my response is usually, I appreciate those images. I really enjoy those images. I wish I could produce those kind of images. But at the same time, I like the images that showed a comet the way it looked to my eye through the telescope, or to my eye, naked eye. I like also having that record of what the comet really looked like. For us looking naked eye, Neowise was visible with a short tail, and that's all it was. And I live in a site that, not the darkest skies, but pretty dark. It didn't have a 30-degree long tail naked eye, at least where I was. So I like having, just seeing his little short stubby tail. And when people show those pictures, I'm like, that's what I saw naked eye. That was my Neowise comet.
What, you mean you didn't see the one with the big spirals? Surely that's what you saw visually.
Exactly.
Which comet, Carl, would you like to, if you could get into a time machine, which comet from history would you have liked to been there to see?
Oh, geez.
I know Dan liked the 1577 one, didn't you, Dan?
See, I mean, I'm young enough where I've never seen a Kreutz comet. Wasn't born for a Kiyosaki. McNaught was too far south. But at the same time, I really kick myself now for not having enjoyed Hale-Bopp more when it happened. Yeah. Just sitting there every night and drawing all the jets. So sometimes I wonder, maybe the comet of 1811 was probably the closest to a Hale-Bopp type comet.
Definitely, yeah.
But then just seeing, I mean, when you hear John Bortle talk about Kiyosaki and saying, it was that tail had such a high surface brightness, it was brighter than the Milky Way. I just sit there going, oh man. I'd sit there imagining, when I'm looking at Neowise, I was sitting there looking over at Corvus going, I wonder what Kiyosaki would have looked like.
Yeah. Exactly.
Yeah. Well, there are going to be more bright comets. It's not a question of if, but when. And, we may have something later this year. They aren't all that rare. We just get frustrated waiting.
Yes.
It's the Lyrids peak tonight. Well, actually, technically the peak's about 1 p.m. tomorrow afternoon. So tonight's the best night from the UK. And I've avoided reading any of the articles because they're always set to light up the sky. And it's like there's nearly a full moon. It's just.
Oh, yeah.
and even at best, it's a ZHR of 15. People are not going to go out and see a fireworks display.
Yep.
Drives me
Whenever
insane.
People come to me going, oh, there's a meteor shower tonight. Should I look at it? I'm basically like, unless it's the Perseids and the Geminids and the moon's not up, the average person, don't bother. Maybe the Orionids when they're good. But in general, there's only 2 meteor showers to look at that are going to be good every time. And again, the moon can't be up.
Yeah.
Yes.
And you really need to be up in the pre-dawn hours to see it best.
Yeah, up in the pre-dawn. It helps to drive outside of town, which is easier here in Tucson. And remember, you need to get dark adapted for half an hour. You can't be staring at your phone and then looking up.
Right.
Exactly.
Yeah, the age of the cell phone.
Yeah.
Yeah.
To be fair, most of the red head torches you buy for astronomy now are so ridiculously bright as well that I usually put in batteries that are on their last legs so that it's a subtle red light rather than a bright red searchlight. They're just too bright.
Yep.
Yep.
A great comment. Oh, okay, you're going to miss it. It was 1811, wasn't it?
Yes, 1811.
Yep. 1811.
Yeah, you're going to miss it, Nick. See, even if you did that, you still miss it. My God. Doctor Who.
You ask a lot of your people on your podcast what comets they wish that they could go back and see. I presume it'd be interesting to see a list. You probably get as many different answers as there are people that you.
I think so. I personally would have loved to come back and done more with Hale-Bopp. Definitely.
Yeah.
Definitely. I rue that one. I missed several nights, and I was younger, and just it's a kicker. Because I
That
got
was
spoiled
one
because
where I spent a lot of time observing it professionally as part of my job.
Yeah.
And I think that
Yeah.
actually took away a lot of the enjoyment of observing the comet.
Yes.
I kind of like Hyakutake happened so quickly, couldn't schedule telescope time. I just got to go enjoy it. I kind of wish I had just enjoyed Hale-Bopp from my backyard.
Yeah.
Yeah,
Which
that's
was the
understandable.
first comet? What was your first comet that you ever visually saw, Carl?
Halley.
86. Yeah.
Yep. I mean, I knew of Iras-Araki-Alcock, but didn't know where to look. I tried for Jacobini-Zinner, fall of '85, but obviously I grew up in New Jersey, not far from New York City, so I couldn't see that one with my binoculars. And then my dad had a old, probably Sears 60 millimeter refractor that I looked through once when I was, I don't know, 6 years old, 7 years old. And then I begged them to let me use it. And I went out, found the Pleiades, and then found Halley. So that was my first comet, was Halley's Comet.
Mm.
Yeah, Kohoutek in January of '74 was my first one.
Yeah.
Nope.
It
Mine
was
was Halley as
Hale-Bopp
well.
for me.
Hale-Bopp, huh? You miss Hyakutake?
I did. I missed McNaught as well in 2007. I'm not quite sure how, but I missed a lot of good ones.
You know, I almost hopped on a plane to Chile for that one. And
Yes.
I was really close because I knew it was going to be bright because I saw it in broad daylight here in January. And I thought, oh boy, I bet the Southern Hemisphere is going to have a really good showing. And I was looking at airfares, and I was getting ready to go down and stay with Bill Liller at Viña del Mar in Chile. What happened was, by the time the reports started coming in, the problem is a comet like that was really at its peak for just several days, and then it started to fade. And that's just the way it was with Comet West, in 1976 too. You just have a few days and then it's gone.
Yeah.
And so it's like, oh, I'm gonna fly all the way down to Chile. But in retrospect, I wish I had done it because I didn't appreciate, that was really a spectacular comet.
Wasn't mostly just the tail visible from the UK of that one? I'm trying to remember reading about it.
I think we got a bit of the very, very low over the horizon, a bit the head and a little bit the tail, but then as it went below for us, it really went crazy for the Australians and New Zealand people,
Right, but parts of the tail was so broad and bright and long that it was visible from some parts of the southern parts of the northern hemisphere.
Yeah.
Like Hawaii in particular. There were some really neat photographs of the tail, coming up above the horizon, kind of like the comet, Chasseau's comet in 1744, where you
Exactly.
we split. That was just amazing.
And it's great. I mean, yeah, because you had the comet of 1744, and you had those nice little wood etchings, and no one could figure out what that was.
No.
What exactly we've seen, these 7 tails going off in different directions. How do you get a comet like that? And then McNaught showed us that's what you were just catching, that kind of long curved umbrella of a tail, and those were individual like striae that were just popping up over the horizon.
Yeah.
You can't imagine how much it must have been such a mysterious object for people in history to try and get their head around.
Yeah.
It's amazing when we do know what it is now.
Yeah. Well, there will be a few more comets coming around, in the next few years. It's just, it's just a question of, are we going to have good clear weather? Are we going to have light pollution, or is it going to be a southern hemisphere or northern hemisphere comet? That kind of thing.
Yeah.
But
the excitement, though.
I'm cautiously optimistic that the 2021 A1 Africano will be a nice object to look at in December. Especially since it's going to have a few magnitudes of enhanced brightness due to forward scattering from dust, because it's going to be at a high phase angle. Of course, in order to be at a high phase angle, it has to be pretty close to the sun, elongation-wise, but hoping that's going to be a good one. Oh, sorry. I said Africano. I meant Leonard. Yes, they both work at Catalina. I meant Leonard. Yes, Greg Leonard's comet.
Yeah, I was wondering there.
Yeah.
Africano.
Yep. Who also discovers comets at Catalina, but yeah, for some reason I mixed up the discoverer there. So yeah, Leonard definitely.
I think it's. Sorry, Nick. Carry on. I was going to say, I think it's a shame that the 2017 K2 Pan-STARRS isn't coming closer as well. That is an incredible object.
Yeah.
Yeah, and it's going to be, it looks like it'll probably peak at 6th, 7th magnitude, but it'll be observed, bright enough to see in small telescopes visually for a long time, like over a year or more.
Yeah.
Right.
Yes.
Yeah, I think that's near its peak brightness.
Yep.
I saw it a couple of nights ago, I must admit.
Yeah, same here.
Yeah. Yes. Yeah.
Yeah. Yep.
We're also due for a really nice bright Kreutz sun grazer one of these days. So.
Yeah. Terry Lovejoy. He had the last one, didn't he? Oh, okay. Yeah, but I think the last one found from the ground was Terry Lovejoy's in 2011, wasn't it? 2011
Yes.
W3? Yeah.
Yep.
The headless comet.
Yep.
It went in with the head and came out with that one.
Yep.
It will be.
Yeah, we certainly see a lot of comets that fall apart.
It seems almost every year we find one now.
Yeah.
Which makes you wonder how many we've missed.
Right.
How many comets we either missed completely or fell apart, and you just said, it just faded quickly. Didn't think much of it.
Yeah.
I mean, when Atlas, the Y4 comet, split up, beginning of last year.
Yeah.
It was kind of a shame because it happened in the middle of COVID. So almost every professional observatory was shut down. And here was like one of the best placed disintegrating comets since the 2000 S4 linear comet, or sorry, 1999 S4 linear comet back in 2000. But the great thing was the amateur community was able to step in and fill that gap and observe the comet and follow it and watch the different pieces, because it was observed for a good month or two after it kind of started falling apart. You can see the individual pieces.
But that is actually fragmented from another comet in the 1860s. Was that correct?
1844, I want to say. Yeah, it was a fragment of a great comet from the early 1800s.
Yeah. So it probably had a bit of, stress fracturing going on there, and it's probably quite weak as it was coming in. But I think it actually did survive perihelion, though, didn't it? I think it did. I
think so. Something still survived. Yeah.
Yeah.
Yeah. Sometimes they completely disintegrate, and quite often there are, long period comets making their first pass, and they're probably really small nuclei. But then you do have these secondaries that came off something larger, and secondaries don't last long. I mean, that's one of Zdeněk Sekanina's research, that they usually don't, not always, but most of the time they disintegrate within at least one or two perihelion passages.
Yeah.
Well, McCoy sun grazers are a prime example of that. Long period comets that come in, and you do have some that survive.
Yeah.
And come back multiple times, even going very close to the sun.
Yeah.
Yeah. And each time they go around, they pretty much break up and produce future smaller sun grazers.
Yeah.
Mm-hmm. Yeah, and the more you look, the more you'll find. I mean, that's OSIRIS-REx with the particles coming off the asteroid Bennu. Now, we don't think it's related to cometary activity, but it shows even relatively inert objects can show what looks like cometary activity.
Yeah, it makes me wonder how many things that have been said to have cometary activity have been caused by something similar to that.
We know some of the main belt comets probably were due to impacts, like asteroid Sheila, one of the larger asteroids, had, looked like a comet all of a sudden for a few months, and that was probably an impact.
Right.
Asteroid Gault had what looks like it's probably rotating so fast, you're getting landslides, you're getting instabilities, and parts of the surfaces are just landsliding down to the equator and off into space. And that's creating these individual tails. So you can have processes that look very much like a comet, but are not, ice-driven, sublimation-driven at all.
Yeah.
So a lot of the asteroids are spinning quite quickly as well, aren't they? Would that throw stuff off more readily? I'm not an expert on asteroids by any means.
So most asteroids larger than about 200 meters, you'll notice they don't spin more rapidly than about 2 hours. Rotation period about 2 hours. And for carbonaceous, that rotation period is more like 3.5 hours, that boundary. And the reason for that is if they spin up faster than that, they will shed pieces. They will actually split, either completely disintegrate or start shedding off pieces, kind of shedding angular momentum, and they'll fall back slower than that that boundary. So all the objects out there all the asteroids over time probably are slowly eroding as they spin up and they start shedding material. The really small asteroids, objects that are smaller than 200 meters or even the size of your office or a desk, they can spin as rapidly as 10, 20 seconds. So there's a little bit of strength holding them together, but not much. Probably most of them, except for maybe the very largest asteroids like a Ceres or a Vesta. Most of them really are rubble piles. The thinking for an asteroid like Bennu, the OSIRIS-REx target, is that it used to be in a much larger parent body. Maybe it was 100 kilometers across. That got impacted by something, completely shattered both those, the impactor and the impactee. And then a lot of the family of objects that came out of that, like Ryugu and Bennu and stuff, just kind of then accumulated back into these smaller objects, which consist of probably most of the original parent, but also material from the impactor, which is why sometimes you get meteorite falls that have multiple different kinds of meteorites within them, carbonaceous, stony, achondrites, and stuff like that. So everything has been jumbled up, and I think most of your objects smaller than a couple 100 kilometers probably reaccumulated from impact debris, from larger impacts that happened.
It's interesting. I made one of the articles that I wrote for Sky at Night was making a model of an asteroid, and I chose Eros. I really liked the shape of it, but I was really struck by just how much kind of loose gravel it looked like it was covered with. And I think I remember reading somewhere that it probably had craters once that seismic activity is shaken down into rubble. But maybe it isn't just that. It may have been an accumulation of other things that, I mean, the surface is just strewn with rubble, the same as the other close-up asteroid pictures we see.
Yeah, when these objects are small and they're all rubbleized, I mean, it's almost like a beanbag. Every time it gets hit by something, it may make a slight crater there, but it kind of erases all the craters and other features around the asteroid because the whole thing, you just kind of shake it up.
Yeah, it was certainly interesting to make a model of, that's for sure.
Yeah. I mean, when we picked Bennu as our target, we were hoping for these nice little sandy, kind of dry lake beds or playas like we saw in Eros. Yeah. And we didn't find that at all. Bennu and Ryugu just had, didn't have much in the way of small sand that we were able to see. It was mostly centimeter or larger rocks all over the place. And not much in the way of craters. I mean, we identified some craters, but they're really kind of eroded and hard to see. And that might just be because these objects get hit by things, shakes them up, erodes things, and also they're spinning fast enough that maybe you're getting what we call mass movement, where material is moving from the poles to the equator, and that's erasing all the features as it moves over it.
It must be quite challenging for the spacecraft as well, because trying to find somewhere to get samples from when it's just this rubble pile must be like quite dangerous for the spacecraft.
Yeah, originally we wanted an area that was safe to land that was about 20 meters across. And then when we got there, we found, whoa, there's really nothing that we can get to that isn't larger than about maybe 6 to 8 meters across. So we did have to kind of redesign the automated terrain recognition software on the spacecraft and give the spacecraft a little bit of smarts about where it was going to land. Not that it could do any course corrections, but we set it up so when we did our burn, we aimed for a target on the surface. It's almost like throwing a dart at a dartboard. The dart wasn't smart enough to make sure it hit the bullseye, but it was smart enough to keep track of whether or not it was going to hit the bullseye. And if it wasn't, it would just abort and go back, and we would try it again.
Was it Bennu or Ryugu that ended up with the sample chambers being absolutely crammed full because there was so much soft material on the surface when it dove down?
That was the Japanese.
Yeah. No, that was ours.
Oh, was it?
That was yours?
That was ours. That was Bennu. So the requirement that we had, our level 1 science requirement, was bring back 60 grams of material. Yeah. Now the head was designed that under perfect conditions, like we ended up hitting, a nice sandy region of the asteroid, we could collect maybe 2 kilograms of material. What happened was, the spacecraft matches the rotation of the asteroid at about 30 meters and then free falls. And it's microgravity, so you're not accelerating to more than maybe a couple centimeters per second when you finally hit the surface. I think it was about 10 centimeters per second when you hit the surface. And what happened was we hit the surface and kept going and going and going. And then the canisters, we had inert nitrogen gas, blew out of the head into the surface and pretty much created a crater that we kept falling into. Huh. So that the head of the sample collector went down about 40, 50 centimeters.
Wow.
Before the thrusters finally engaged and we pulled out. And so there was almost nothing there holding us back. The asteroid was giving way. I mean, if the thrusters hadn't engaged, would we have gone completely into the thing? mean, there was
Wow.
very little strength there. And so we ended up collecting so much material that there's a little mylar flap that was supposed to kind of snap into place and hold all the material in. And the sample head was overflowing, so the mylar flap never closed. And the test we were going to do was this, first take a picture of the head, see if there's anything in there. And then we were going to kind of do this moment of inertia test that we had done with the sample arm and head empty, and then we were going to do it full to kind of measure how much material we had. And just taking those first pictures, just moving the arm a little bit was enough to throw material out. And we probably lost as much material moving the arm around a little bit as our original baseline.
Gosh.
Wow.
And so we went to NASA and we said, can we stow like now before we lose all our material? And they're like, go for it.
Wow.
Yeah, I saw a talk a couple of weeks ago on asteroid sample return missions, and they talked about that there, and it showed the video of the stuff just coming out and the flap not closing.
Yeah.
Hairy
And it was great
moment.
because we now have images of the sample. I mean, it's the escaped sample, but we have images of the sample that are pixels across. So we actually have some shapes, albedos. So we can do sample analysis now based on the samples that escaped that we were able to take pictures of.
Excellent.
And of course, there was a program made called Touching an Asteroid, which I think you're actually on, Carl, aren't you?
Yes.
That's a great one to watch. We've just got that here.
Yeah, Nova special.
Yeah. Yes, you can. Yeah, I got it myself the other day. Fascinating.
Yeah, that was a fun one because, the mission launched in 2016. And for a lot of those, we were filming going back, 4 or 5 years. So it's kind of cool to,
Yeah.
do all these interviews over time. And then as you're making discoveries, and they were there when I kind of made the announcement, oh my God, guys, the asteroid's blowing up, it's shooting at us. Which right. Yeah, we were always so worried about not collecting enough material or not knowing whether or not we collected any material. Like we wouldn't see evidence of our actual collection event. And as it turned out, it was the extreme that we had to worry about, being too successful. Yep. Yeah, and the next big sample return mission, I believe, is the Japanese MMX mission, which is going to go to Phobos and bring back a sample. Is Phobos a captured carbonaceous asteroid, or is it really just debris from Mars? Right. Yes, that'll definitely be an interesting one. And the Japanese have another mission. It's not a sample return mission, but a flyby mission called Destiny Plus, which is going to fly by Phaethon, the Geminid parent body.
Yeah.
Yep. Here's an object that still releasing meteoroid particles, so only when it's at perihelion, which is really close to the sun. So that might just be you're so close to the sun, solar wind is sweeping over your surface, knocking particles off, or you're actually just getting particles just thermally dissociating because it's so hot and popping off the surface. But also there's no evidence of hydration on the surface. The asteroid, at least the surface, is bone dry. So maybe here's an object that used to be more cometary hundreds of thousands of years ago, but because it gets so close to the sun, the surface regions have potentially dried out. So kind of the first time we're going to an extinct comet, assuming it's even a comet. It could be something, most likely it originated in the main belt.
Yeah.
But then now the studies are suggesting that the primordial stuff that we find in the main belt today wasn't there in the beginning of the solar system. It got all kicked out. and new material was trapped in there. So some of those carbonaceous asteroids might actually be related to more traditional comets. It's just they've spent the last 3-4 billion years, 2-3 AU from the sun. So they just look different. Yeah. And then the Lucy mission, which is another NASA mission, will be flying by a whole bunch of Jupiter Trojan asteroids, which, here's again, carbonaceous cometary material that's been stuck in deep freeze at 5 AU for most of the history of the solar system. Right. Yeah, and I mean, there's the Comet Interceptor mission, which I think is a UK-run mission. Okay, European Space Agency mission that, once it's up there and does have the ability, if you do get another Borisov, to potentially be redirected to fly by one, either a long period comet or, like another Hale-Bopp or potentially an interstellar one, assuming you can catch those interstellar ones with enough lead time, which is a little tough to do. They move so fast.
Yeah.
Yep. Yeah, and then we get to look forward to the Rubin telescope and maybe even NeoCam or NEO Surveyor is the new name for it, in the next decade or so. And they'll go significantly fainter and catch a lot of objects, with enough lead time.
No, I was just going to mention Oumuamua, of course. I just wonder what Carl's thoughts were on Oumuamua. We've mentioned Borisov, but what was Oumuamua?
That is a good question, because that sure is an interesting object. I mean, with the weird shape and even the weird colors, that's one where I'll have to admit I really don't have an opinion. I just kind of been enjoying just reading the literature as people trying to wrestle with exactly what was this object we saw. I think a lot of it is just you can only observe it for a short period of time before it got too faint. And of course, you needed a gigantic telescope to get any real science on it. But yeah, to see an object that's that elongated, rotating that fast, that was an interesting one. Mm-hmm. Oh, yeah, they would they would have the technology to make sure we didn't detect it. And plus, why would you make it so weird shaped? You would just make it round like a regular asteroid or something like that. But yeah, I believe it's natural. It's just exactly, and it's probably just a comet from a different solar system. And again, I mean, we know comets that have been in the main belt for billions of years look different than comets that were spent their time in the Oort cloud or the Kuiper belt. So maybe comets that spend billions of years floating in, interstellar space they have another difference. They just look different. something's going on.
You know, think about a murmur. You mentioned before about the way that certain things spin can send material to the poles. Could that possibly over time cause an elongation of something? It really was such a strange object.
It can. So usually once it spins up too much, they'll start shedding material and breaking apart. It would have to have some pretty strong internal strength to hold that shape.
Yeah.
I hope we get another one.
Right.
It's amazing. Yeah, we should let these guys go.
Yes.
Sure, I'd be happy to.
Yeah, definitely.
Okay.
Good night from me.
Thank you, everybody.
Yeah, thanks and good afternoon.
Yeah. Thank you, Dan. Thank you, Carl.
Very good. Thank you.
Sounds great.
Bye.
Good night.
Bye.
Bye-bye.